understand the applications of Ampere's circuital law. The Ampere's circuital law is the magnetic field over the entire loop or the entire line of loop is mu naught into I. I is the current passing through that plane of loop. Let us understand the different situations where the currents in different amounts or different directions. Here is the current is passing through the plane. Current is I. When you apply this Ampere's circuital law for this diagram, it is mu naught into I. That is magnetic field over the line or the entire line of loop is mu naught into I, because only I is the current passing through the plane containing this loop. In this plane of loop, there are two conductors carrying currents I1 and I2. Two currents are passing through the plane. One is I1 and other is I2. What is the total amount of current passing through the plane? It is I1 plus I2. That is I1 plus I2 is a total current inside. So it must be mu naught into I1 plus I2. This expression equals this. In this case, again two conductors passing through carrying current I and I, same current. Then the total current is I plus I, same direction. It is 2I. So it must be mu naught into 2I. But this case is one conductor carrying current in this direction, other one is carrying in this direction, different directions. But currents of different amounts. I1 is greater than I2. We need a net current passing through the plane. The net current passing through the plane is I1 minus I2. Net direction is this. So total current is I1 minus I2. So it must be mu naught into this. What about the case like this? The two conductors, here the two conductors carrying same current, but the current amount remains same. I is this direction, the same current in this direction. When you look at that net current passing through the plane is I minus I. The current is in this direction, same current flows in the opposite direction. Net current is 0. Therefore, it must be 0. This is one different one. Currents are passing, but not through the plane enclosing that loop, but outside the loop. What about the magnetic field over the line? 0. Because the law itself says the magnetic field over the line means the current inside only when the current passing through the plane enclosing that line. But these are not passing through the plane, outside the plane. So magnetic field over the line is 0. Just to understand the exact meaning of what is Ampere's circuital law. This is about the loop. I have taken in that circular geometry, circular shape. We can have the loop or what is that, the closed loop of any geometrical shape. Here the geometrical shape is circular shape. It can be an elliptical form, elliptical shape, ellipsoid. It can be a square, that is four sides squares. It can also be a rectangular. See, and all of them have symmetry. The shapes have symmetry. So we can choose what is that, the shape of the loop of any configuration, maybe circular or elliptical, square or rectangular. It can be applied. The law can be applied to that loop of any shape. Now let us understand the magnetic field, that is magnetic field produced by the conductors of different configurations. The conductors of straight line here. Let us see different configurations. Look at this configuration. This is a conductor of what is that, circular conductor. Configuration is circular shape. If the conductor is like this, what would be the magnetic field? It is already being taught. The magnetic field produced by the circular conductor is these magnetic lines. I am showing that. These are the lines. The straight line along the axis, and the lines, magnetic lines, are bending away from the axis in different angles depending on the distance from the center. And the direction of magnetic field is related to the current flow. If the current flow in the circular shape is in anti-clockwise, the magnetic field direction is this, like this. So there is always a straight line along the axis of the circle, like this. This is one configuration of conductor. Let us understand another configuration of the conductor. Here, the electrical conductor of some configuration. What is this configuration? The diagram. In the diagram, you have taken a cylindrical shape material, a material of cylindrical shape, which must be a non-conducting material. See that around which the conducting wire is wrapped tightly. The conducting wire is wrapped tightly in spiral pattern. That is like this. Spiral pattern. Spiral pattern. It is around the cylindrical material, which must be a non-conducting substance. So we have what is that, number of turns in the spiral. What is that? In what is that, spiral in longitude like this. Number of what is that, circles like this. Spiral circles along the line. So each one is called as one turn. And L represents the length of this what is that, cylindrical material. If you do so, that is wrapping the wire tightly around the cylindrical material in spiral pattern, that may produces or create what is that, a coil. That is, coil is known as solenoid. The name it is known, it is called as solenoid. What is solenoid? It is a coil, electrical coil. How you produce it? Just by wrapping the conducting wire around what is our cylindrical material in spiral pattern like this. And length is L, L stands for length of the solenoid and capital N stands for number of turns. Each round is one turn. Number of turns along the L. So this L contains N number of turns. This N number of turns is the solenoid. What happens when the current is passing through the wire? That is, wire is in the spiral direction like this. If you suspend this solenoid freely in the space without attaching anything to it, freely floating in the space, if this is held freely in the space, just like floating a material in the space, and upon passing current, that is through this wire and coming out here, electric current flowing here, electric current coming out, and electric current is steady along all the wire. Right. What happens? It will be oriented in north and south direction. Exactly behaves like a bar magnet. As you know, the bar magnet has, there are two polarities, north polarity and south polarity. Here the current is flowing, what is that? At the back of the cylinder, the wire is not shown, it is in front of the cylinder. Back electrical. Current is what is not flowing in this direction, up and down, front side, up, back side, down like this. And each turn produces a magnetic field like this. There are n number of turns, that is, in the same pattern, what is that? Each turn produces the magnetic field in the same pattern along the axis, because all the spirals are on the same axis. So each turn produces in the line like this, and we say n number of turns, all of them produces the same lines like this, and magnetic field, what is the magnetic field? Along the axis of the solenoid or inside the solenoid, it is intensified, it is getting multiplied by each spiral. So magnetic field lines, what is produced like this in the same pattern like this. Here by single circle, here by many circles. So this, what is that? Intensity of the line, it is quite bigger than the intensity of the line what you see here. Magnetic field intensity inside, you see that along the line, it is intensified or multiplied in the space. So this is the magnetic field inside the solenoid. Straight line along the axis B. So here it like north pole. This material solenoid is north direction, is south direction. This is electromagnet, just like electromagnet, and behave like a power magnet. This end is north, this end is south. It will be directed north to south if the current is passing through it and held freely or floating in the space. That is why. Suppose if you reverse the direction of the current, so instead of passing like this, if you pass in the reverse direction, what will happen? It is again a magnet, changes the polarity, that is, north becomes south, south becomes north. Then it will change the direction of orientation. As a result, it gets what is rotated. Solenoid rotated through 180 degree upon reversing the current. That is an experimental evidence to show that a coil like this exactly behave like a magnet, bar magnet. It is electromagnet, that was a natural magnet. So this is about the solenoid, construction and working of solenoid and electromagnet like this. Now we have to obtain the expression for magnetic field at any point along the axis of the solenoid. Here it is, magnetic field is quite stronger. Let us estimate or Find the expression for magnetic field at any point along the axis using Ampere circuit law. For this, we require these diagrams. This is a diagram to understand. Look at that. In the direction of the current in each loop, just what is that? Using same what is that? Right hand palm rule. Look at this. Wire at the back of the cylinder. Direction of the current is upward, like this. So palm rule is, if you what is that? Outside, the line is back side. Direction is current. Direction is this, and the moving fingers like this inside, like this. Even if you take here this side, the same spiral binding, this portion, direction is this. So here what is that? Holding the finger like this, thumb in the direction of the current, and move the what is that curling fingers like this, again inside, like this. So like that, at each turn we have to calculate that magnetic field is along the same, what is the inside only, not outside. Using right hand palm rule also, we can understand the direction of the magnetic field in the solenoid. That is the one. And this is about the diagram. What is the diagram? This diagram is exactly what is that? If we cut this solenoid into two equal halves like this, the same what is that? The solenoid into two equal halves. One is that side, other is side. If you remove this portion, two equal halves, remove this portion, the remaining portion at the board is this, like looks like this. Here the wire coming from the back side. Here wire is what is that? Moving in this direction. So this shows that here the symbol shows that circle with dot, circle with dot, circle with what is that? Cross mark. So it's all indication of the direction of the current. So and also the indication of the direction. You can use the same symbol for direction of the magnetic field, direction of the current. But direction of the current I am talking about here. Here you cut into equal halves. One portion is removed, other portion is always attached to it. Here the current in the outward direction. Movement is outward direction from plane. Here current is like this. Current is inward direction. So that direction of the current with this geometry that is inward. Direction is outward. This symbol. From all this current is outward. From all this current is inward. This R stands for radius of the solenoid. This is axis of the solenoid. This is section. What is that? Diagram showing cut section. And now I am taking. Our aim is to find out the what is that magnetic field along the axis. For that we have to use this Ampere circuit law. We are using one ideal. What is that? Ideal loop. This ideal loop means rectangular loop. Plane. A rectangular loop I am considering. This rectangular loop enclosing a plane. That is a plane. So what is the plane actually? This plane is inserted into the solenoid like this. This rectangular plane of loop is bisecting the solenoid like this, exactly off. This is what is I said. Rectangular plane of loop bisecting the solenoid along its axis, so that the sides AB and BC stay outside the solenoid on either side of the side. So rectangular plane of loop is inserted like this in the plane like this, so that this side stay behind and this side stay in front, away from the surface. They are away from the surface. This is the line of what is that? Axis of solenoid. So we are taking that loop. What is that? I already said you can take any configuration. I am taking rectangular loop to calculate the magnetic field. If you do so, if this is inserted like this, look at that. The wires are what is that? Back side coming up. Here current is coming. Current is moving up. Front side current is moving down. If you cut it like this, see that current is what is that? Passing through the plane. Back side now in this direction. Through the plane, what the current flowing, what is that from the back of the wire is actually what is that? Current is flowing through the plane upside. All the currents, there are number of turns. In the front side, what is that? Same direction is reverse, downside. Current is passing through the plane in the downward direction because of these wires. Look at the direction and passing plane. Plane is bisecting the. So look at this with this diagram, you can understand what is each current is that current strength is I all over. Each wire carrying I current, its total current is Ni. And same number of what is turns are there now, same number of Ni. Your Ni current in one direction, Ni current in the opposite direction, similar to this. If that is the case, what is the magnetic field along this loop of the line? There's zero. The same concept you apply. That means AB is outside the solenoid. DC is outside the solenoid. If any, what is that? Any point or any line staying outside the solenoid, that is magnetic field is zero. What I said here. Net current passing through this in accordance with the Ampere circuit concept of, that is Ampere circuit law says that regarding this geometrical shape of the loop, the magnetic field is zero by this loop of line like this. If we insert a rectangular plane in such a fashion, now with this we understand what is that? Any point or any line outside the, what is that? Just staying outside the solenoid, magnetic field is zero. Just to understand the point, we have used this diagram. Let us use the same kind of diagram, but bisecting. Look at that. What is that? Half of the solenoid. That is, plane is passed. Here bisecting means only this portion I am taking. So here, this portion, what is that? The only plane of this portion. So this side DC, here is staying along the axis of the, use the plane which bisects half of the solenoid, like this. So that this side stays outside the solenoid, and this side of the rectangular stays along the, what is that? Along the axis of the solenoid. Only half of the rectangular. So now it is back side, its plane is back side and up to axis. No further extension of the plane in front. Here this is removed. Only this one. This is again a rectangular plane. Very important. This is a diagram you need to understand. I am taking this rectangular plane of loop. This is important. So with this, what is that? We have current passing through only what is that? One direction. This is not there. This plane is not taken. Removed. I am taking only this plane. Current passing through the plane of this rectangular loop in one direction. N number of currents, Ni. So this loop produces the magnetic field. Magnetic field about these lines. Magnetic field over the line, entire line of the loop you have to calculate, because it's only one direction passing through the plane of this loop, only one direction. So when you look at this magnetic field, this loop is not like circular, it are different directions, rectangular. This is a magnetic field due to this line, magnetic field due to this line, magnetic field due to this line, magnetic field due to this line. You need to understand that. Already I said this line is always outside this solenoid. Magnetic field due to this line is 0. And see that in later how do you calculate. So we have to, using this diagram, we can calculate the magnetic field over the entire loop. How do we calculate? That is a calculation go for calculation. This is what I said about the second diagram, rectangular plane. Bicycling the solenoid along the axis so that the side AB stays outside and the BDC stays along the axis. So I am taking the figure 2 for the calculation of magnetic field. That is according to that is integral of the circle, entire loop, this into this vector equals. So we have not that uniform line. There are 4 different lines are there. That is circle, that is loop contains 4 lines. D to C, magnetic field over the line plus magnetic field over this line plus magnetic field over this line plus magnetic field over this line. We have written all the 4. D to C 1, C to B, A to B, A to D. Same factor, 1, 2, 3, 4. D to C, C to B, B to A, A to D. Now to first calculate what is that. What is the magnetic field due to this? C to B. C to B means this is C to B. Here magnetic field is what is D, DL is this direction. Both of them are the DL is this direction, magnetic field is this direction. Look at the magnetic field. Magnetic field in this geometry is only along this line, and field length, the length of the conductor or length of the loop is this DL. They are perpendicular 90 degree between these 2 lines. Therefore cos 90 is 0. Cos 90 is 0 means this must be 0. Similar case for A to D. This line is perpendicular to magnetic field. So DL along the where? DL. So many DLs are along this DL direction and field directions are perpendicular. Again 0. Magnetic field due to line is 0. Again 0. And the second one, C to B, A to B, I said this line is staying outside the solenoid, definitely along the line. What is that? A to B, this is 0. Of course, it is same line, different direction, but outside it is 0. So all of them, all this in all the summations, these functions of 0, only remaining function is this. So total magnetic field about that loop is only magnetic field along only one line, net magnetic field. So apply this equation. This is same as this D to C, and B is the magnetic field. Apply this definition of dot product B into DL into cos theta. Cos theta means their theta DL and B. DL and B, L and B are in the same direction. Theta equals 0. Theta equals 0 means cos 0 equals 1. Only B and DL remains along DC. So B is constant at every point on the line. So B into integral of only DL. From D to C, it is integral of DL is L. D to C, what is the length? Length is length of the solenoid. Total length. Total length of DC is same as length of the solenoid. B into L, it is right hand side of the Ampere circuit law, right hand side. So left hand side is mu naught into I. Here current is not simply I here. How many highs are possible? So many lines are there. N number of lines. Total current passing through the plane is Ni. N number of turns we have. N into I. Inside, I inside. So this expression is got finally B equals, simplify this, L goes to denominator, mu naught Ni divided by L, and B equals N by L, that is total number of turns divided by the length of the solenoid. It gives what is that number of turns per unit length. N divided by total number of turns divided by the total length of the solenoid is number of turns per unit length. N stands for number of turns per unit length. Mu naught into N into I. What is the magnetic field at any point along the axis of the solenoid? Magnetic field at any point along the axis of the solenoid. Strong magnetic field is there. It is always mu naught into N into I. That is amount. It depends on the amount of current passing through the coil and number of turns it carries, or number of turns per unit length. If you have what is that closely wrap, gives more number of turns per unit length. If N is more magnetic field. I is more magnetic field. There is an expression. You can easily apply this to any concept, any configuration like this, and get it like this. You can also get the same expression using Biot-Savart's law. Derivation is different. It's a laborious mathematical differentiation. Mathematical evaluations is a bigger process. You get the same expression either way. So using what is our Ampere circuit law, we can get a derivation for the expression, derivation or expression for B along the axis of a solenoid. So this is about the solenoid, the construction, working and evaluation of magnetic field along the axis of the solenoid. It is electromagnet. If you replace by non-conducting material by what is a conducting material of any kind, what is that? A strong paramagnetic material. It is ferromagnetic material. It is magnetic field is further increased. It support magnetic field. So with this you have completed this concept.